All right, ready for a deep dive. Today, it's the world of statistics. We're looking at the Cartoon Guide to Statistics.
Cartoons and statistics, huh?
Yeah, it sounds a little odd maybe.
Yeah.
But this book, trust me, it makes it all, even if you hate numbers, really approachable.
It does. It really does. Uses humor, visuals, breaks it down, makes it fun.
Exactly. So we're trying to get to those fundamentals of statistics, right? What they are, why they matter, and how do we even make sense of all this data?
It's more than just numbers. This book makes that clear. It's about, understanding uncertainty, making decisions when you don't know everything.
Making better decisions.
Yeah.
I like that. The book even mentions some, I don't know, kind of dramatic examples, right? Like the Challenger disaster.
Yeah. The Challenger, that's a cautionary tale, right? The engineers, they had noticed this correlation with low temperatures and the O-rings failing.
Oh, right.
But that information, it didn't really get to the people making the decisions. And it's a tragic example. You can have good analysis, sound analysis, and it's useless if it isn't clear, if no one acts on it.
Wow, yeah. Really makes you think.
Yeah.
But there are positive uses of statistics too, right? Not all doom and gloom.
Oh, absolutely. Think about, the Salk polio vaccine trials. Those relied on statistics heavily to show it worked.
Okay, so we're talking preventing disasters, developing vaccines. That's pretty impressive.
Yeah.
But the book also talks about how statistics can be misused, right?
Right. Lies, damned lies, and statistics, right. That's why understanding the fundamentals is key. So you don't get fooled. You can make your own decisions based on, evidence.
So where does this book even begin? It seems like the first step's got to be organizing the data, right?
Yeah.
Making sense of it all.
It is. And the book starts there with data description, different ways to visualize data. Histograms, stem and leaf plots, box and whisker plots, all kinds of things.
Right.
Each shows you something different about the data.
Speaking of stories, I loved the example of Florence Nightingale.
Oh, yeah.
You wouldn't think of her as a data person, but...
Yeah. No, not really. But she was a pioneer in using data visualization. During the Crimean War, she used charts and diagrams, showed the horrible conditions in those hospitals. Powerful visualizations, they led to changes, saved lives.
That's pretty inspiring, honestly. But visualizations they're great for quick overview, but sometimes we need the numbers themselves, right?
We do. And that's where summary statistics come in. Numbers that capture the key features. Mean, median, standard deviation, interquartile range.
Okay, I've heard those terms before, but I'll admit I get them mixed up. Can you give me a quick, refresher?
Yeah.
The difference between, say, mean and median.
Sure. So the mean, think of it as the balancing point on a seesaw. It's the average, the median, that's the middle value when everything's lined up in order. Then you've got interquartile range, that's the spread of the middle 50% of the data. Standard deviation is how much the data points are, deviating from the mean.
Okay, it's starting to make more sense now. So the mean is like the center of gravity, and the standard deviation tells you how spread out everything is. And that matters for understanding all sorts of stuff, right?
Yeah, all kinds of things. Investment risk, polls, you name it.
Speaking of interpreting data, the book goes into probability. And it's surprisingly fun. Uses games like dice and cards.
It's a great way to get the idea across because probability is really about understanding the chances of different things happening.
Like figuring out your odds of rolling a 7.
Exactly. And the book even gets into this historical gambling problem that, it actually sparked some mathematical breakthroughs.
Wait, hold on. A gambling problem led to breakthroughs in math. That sounds interesting.
It does. So this problem, it was about splitting the money fairly in a game that got interrupted. And these two mathematicians, Pascal and Fermat, they started writing letters back and forth about it. And that led to, basically modern probability theory.
Wow. So a gambling argument basically changed math. Amazing.
It is. Shows how even simple questions can lead to big discoveries.
Okay, so data, stats, probability. Where do we go next?
From the concrete stuff, like cards and dice, to something a bit more abstract, random variables.
Oh boy, random variables. Those are always a bit tough for me. Can you break that down a bit? Why do they matter?
Think of an experiment, right, where you don't know the outcome for sure, like flipping a coin, rolling a die. A random variable, it just assigns a number to each outcome. So heads could be 1, tails 0. Now you can measure things.
So you're turning randomness into something we can analyze with numbers.
Yeah, exactly. And once you have that random variable, you can look at its properties, like its probability distribution, its expected value, its variance, and those tools help us understand those random things happening.
So like with the coin, the expected value would be 0.5, right? Equal chance of heads or tails.
You got it. And this idea of random variables, it's a big deal. Understanding hypothesis testing, regression, all that stuff builds on it.
It's like the bridge from basic probability to the harder stuff, right?
You could say that. Let's just go from individual outcomes to the big picture, the overall patterns.
So how does the book build on that? Does it talk about different kinds of random variables?
It does. It
Yeah.
gets into two key types, discrete and continuous. Discrete, that's when it can only be certain values, like how many heads you get in 10 tosses. Continuous, it can be any value in a range. Height, temperature, things like that.
So discrete is counting, continuous is measuring.
Pretty much. The book uses, again, simple examples, coin tosses, spinning things, and it's important to get this difference because it changes how we analyze the data.
Okay, starting to see how all these pieces fit together now, like building a toolkit.
That's a good way to put it. And the book, it's doing a good job of giving you those basic tools.
So what's next in the toolkit then? Where do we go from here?
Well, it goes into two specific types of probability distributions, super common ones, super important ones, the binomial and the normal distributions.
Okay, normal distribution, that's the bell curve, right? I've heard of that.
Yeah.
But binomial, less familiar.
Yeah. So the binomial distribution, it's all about those repeated trials where there's only two outcomes, like flipping that coin. And it tells us the probability of getting a certain number of successes, like 7 heads out of 10 flips.
So it's a shortcut for figuring out those probabilities.
You got it. Now, the normal distribution, that's that famous bell curve. You see it everywhere in nature. Heights, weights, test scores, even measurement errors. And it's important because of something called the central limit theorem.
Central limit theorem. Vaguely remember that from stats class. Something about averages, right?
Yeah, you're on the right track. Basically, it says if you've got a big enough sample, even if the original data is not normal, the averages will look like that bell curve.
So even if individual data points are all over the place, their average is predictable. That's interesting.
It is, right. And that's why the normal distribution is so powerful. We can make guesses about whole populations just from samples.
This is starting to all connect now.
That's what statistics is all about.
Okay, so we've got data, summaries, probability, random variables, now binomial and normal distributions. What's next?
Well, from the theory, the book moves to the real world, sampling.
Makes sense. We can't always measure everything, right?
Nope. We can't measure every pickle in the jar to find the average size. Got to take a sample.
Exactly.
And that's where different sampling methods come in. Simple random sampling, stratified sampling, and more. And the book explains all that. And it gets into sample size, too. How big your sample is, that's key for being accurate.
It seems like there's a lot to think about with sampling. How do we even know if our sample's any good?
That's the question. And that's where we get to the standard error. It measures how much those sample estimates might be off from the real population values. Helps us know how much to trust those results, how big the margin of error is.
So it's like a reminder that our sample's just a snapshot, right?
Yeah.
Not the whole picture.
Exactly. Understanding the standard error, it's crucial for interpreting any results you see.
This is so helpful. Feeling like I'm actually understanding statistics.
Yeah.
But we're just getting started, right?
Oh, yeah, there's so much more to it. But these ideas, they're the foundation. And that's where we get to, some really important stuff, confidence intervals and hypothesis testing.
Confidence intervals, hypothesis testing, those always sounded so intimidating to me.
They do sound like that, yeah. But they're really just tools for making, I guess you could say, educated guesses about that whole population.
Educated guesses. So we're like detectives, right? Using data instead of fingerprints.
Yeah, I like that. You're trying to solve the mystery of the population, but you only have clues from a few witnesses.
And the confidence intervals like narrowing down the list of suspects.
Exactly. Let's say you want to know the average height of all the students at a university, right? You take a sample, find the average height of that sample, and then you make this confidence interval. It's a range where we think the true average height of all the students is.
So instead of saying the average height is this, we say we're pretty sure it's somewhere between this and this.
Right. And we decide how sure we want to be, usually 95% or 99%. That's the confidence level. It's like saying 95% sure the culprit's hiding in this neighborhood.
Okay, that makes sense. But what about hypothesis testing? Where does that come in?
Hypothesis testing, that takes it a step further. Like now we're putting our suspect on trial. We start with a claim about the population. We call it the null hypothesis. It's basically saying nothing interesting's going on.
So like the average height of all the students is 5'8", that kind of thing.
Yeah, exactly. And then we use our data, see if we have enough evidence to throw that out, to say, nope, our suspect's probably guilty.
And how do we decide if it's enough evidence? Is it like beyond a reasonable doubt?
It's a good analogy. We look at the probability, the chance of getting our results. If that null hypothesis was actually true, if that probability is super low, below some threshold, then we say, hold on, something's not right here. We reject that null hypothesis. There's got to be another explanation.
It's like finding a smoking gun.
Yeah, exactly. Now, I got to remember, even good detectives make mistakes.
Oh, you mean like convicting an innocent person?
Yeah.
Or letting the real criminal go free?
Yeah. In statistics, we call them type I and type 2 errors. Type I is like a false positive. We reject the null when it was actually true. Type 2, that's a false negative. We don't reject it when we should have.
So how do we avoid those mistakes? Get better at our detective work.
One thing is that significance level, that threshold we talked about. If we make it lower, harder to reject the null hypothesis, less chance of a type I error, but could make it easier to miss a real effect. That's the trade-off.
A balancing act, huh?
It is. And the other thing is the power of our test. How good is it at finding a real effect? A high-power test, that's like a super sharp detective, picks up on the clues.
Like Sherlock Holmes.
Exactly. And the book talks about how that power depends on a few things. Sample size, the effect size, the variability in the data.
Okay, so good detective work means choosing the right significance level, using a powerful test, and having enough data. Got it. So where do we go from here?
Well, so far we've been talking about single variables. But what about comparing two groups? Seeing how two things are related, that's what's next, comparing two populations.
Right, like, is this medicine better than that one? Or does exercise affect heart health? That kind of thing.
Exactly. The book gives us a bunch of tools for comparing groups, whether it's proportions, like what % of people get better, or means, like average scores.
I remember that example, the aspirin study.
Mm-hmm.
Comparing heart attack rates.
Oh, yeah, that's a classic one. Comparing proportions, they found a difference, statistically significant, meaning it probably wasn't just random. Aspirin seemed to help. And the book explains how to do that for means, too, with big samples, small samples.
There was another example that stuck with me. Comparing gas mileage in taxis, using two different fuels.
Oh, right.
But instead of just giving different fuels to different taxis, they had each taxi use both fuels.
That's called paired comparisons. Really clever. By using the same taxi, they got rid of a lot of the variation. Like if you had the same witness for two different events, their comparison would be more reliable.
Controlling for all the other stuff that could mess things up.
Exactly. So that leads nicely into experimental design. If we're doing an experiment to compare, how do we design it well so we can trust the results?
That's a good question.
It is, and there's a whole chapter on that. 3 key things: randomization, replication, local control.
Okay, break it down for me. Randomization, that's like shuffling cards.
Exactly. You randomly assign the treatments, whether it's people, plants, whatever. That way, any differences you see, it's probably because of the treatments, not something else.
Okay, and replication?
Replication, that just means doing it multiple times with different subjects, gives you a better idea of what's really going on, how much variation there is, like getting more witnesses, more accounts, makes it more believable.
More data, more confident conclusions.
Yeah.
What about local control?
Local control? That's about minimizing all the other stuff that could affect the results. Grouping similar units together, like in the taxi example, each taxi was its own group. Reduces the noise, helps you see the real differences.
So it's like making sure you're comparing apples to apples.
Exactly. Those 3 things, randomization, replication, local control, they're the foundation of good experiments. Makes the results, trustworthy.
It's like building a good, solid foundation for our statistical house.
I like that.
So, confidence intervals, hypothesis testing, comparing stuff, designing experiments. What's the grand finale? Where does it all end?
Last chapter is all about relationships. Regression analysis.
Regression analysis. Remember those graphs with the lines through them? Always seem kind of mysterious.
It can seem that way. Let's say we're looking at height and weight, right? You collect data, plot it all, height on one axis, weight on the other, get this scatter plot, all these points. Regression finds the best line that fits through those points, shows us the trend.
So that line, it's like a summary of how the two things are related.
Exactly. And it's a specific line called the regression line, has an equation. We can use it to make predictions, understand how the variables work together. The slope of the line, that tells us how much one thing changes on average when the other one changes.
Steeper the line, stronger the relationship.
You got it. And there's also this correlation coefficient, we call it R. It measures how strong the relationship is and what direction it goes. 1 means perfect positive relationship, -1 means perfect negative, 0 means no relationship.
So it tells you how well those data points fit to the line, right?
Precisely. And regression, it's not just describing the relationship, it's also about making inferences. We can do statistical tests, see if that relationship is real, not just random chance.
Like, is there really something going on here, or is it just a coincidence?
Exactly. And we can make confidence intervals, too, for the slope, for the intercept. Gives us a range of plausible values.
So we could say we're 95% sure the true relationship is somewhere between these two lines.
Exactly. And one of the coolest things about regression is we can use it to make predictions. Like, if we know someone's height, we can predict their weight based on that model we built.
It's pretty neat. But I'm guessing there's a lot more to regression than we have time for here.
Oh, yeah, tons more. The book's just the basics. But it lays the foundation for all that.
This has been quite a journey, feeling like I've actually learned something. It's amazing how much this book covers and still keeps it, I don't know, fun.
It is, isn't it? Statistics doesn't have to be scary. It's a way to explore the world around us.
There's still more to unpack here.
There is. It kind of hints at some more advanced stuff, like different ways to show data when you have lots of variables. Remember those Chernoff faces?
Oh, yeah, those are cool. Using faces to represent data points. It's like data art.
Right. Makes it easier to grasp. And it mentions some other techniques, too. Cluster analysis, discriminant analysis, factor analysis, all kinds of things.
Those sound intense. What can you tell me about them?
Well, think of it this way. Imagine you're, I don't know, a marketer. You want to understand your customers, right? Cluster analysis. That helps group customers together who are similar. Finds those hidden segments.
So instead of just a bunch of individuals you see, like budget-conscious millennials or luxury shoppers.
Yeah, exactly. And then you've got discriminant analysis. Think of college admissions, right? They're trying to predict which students will do well. Discriminant analysis, that helps figure out what factors really matter, what separates the successful students.
So it's like building a profile of the quote-unquote ideal student based on all that data.
Right. And then factor analysis, that helps simplify things. Imagine a survey with tons of questions. Yeah. Factor analysis can find the underlying themes, the attitudes that those questions are really getting at.
It's like finding the signal in all the noise.
Exactly. Makes it all more manageable.
This is making me realize statistics is way bigger than I thought. Yeah. It's not just averages and stuff. It's this whole toolkit.
It is. And the book even mentions some really specialized areas. Time series analysis, image analysis, even resampling techniques.
Resampling techniques. What are those?
So imagine you have this like weird data set, right? Small or unusual. And the normal ways of doing things, they don't quite work. Resampling, it uses computers to make lots of simulated data sets based on your original one. And that lets you estimate things better, more reliably.
So it's like running the experiment 1,000 times in a virtual world.
Yeah, that's a good way to think about it. Takes more computing power, but it can be really useful.
This has been an incredible deep dive. But before we go, I'm curious, does the book talk about any, I don't know, bigger picture stuff for anyone working with data?
It does. It stresses how important data quality is. You know, garbage in, garbage out. If your data is bad, the analysis won't be good no matter how fancy you get.
Makes sense. Can't make a good cake with rotten eggs.
Exactly. Got to collect the data carefully, measure accurately, record everything properly.
So it's not just about the numbers themselves. It's about what they mean, where they came from.
Right. And the book also talks about communication. You can analyze all you want, but if you can't explain it clearly, it's useless. You got to translate that data into something people can understand.
Like being a data whisperer.
Something like that. And that's super important these days with data everywhere.
Well, I'm convinced. Statistics isn't just for academics, it's for everyone. It's about making sense of things, making better choices.
Couldn't agree more. And this book, The Cartoon Guide to Statistics, it's a great way to start exploring. Proof that learning can be fun.
Totally agree. I'd recommend it to anyone who's ever been scared of statistics, or even if you think you know it all, there's always more to learn.
And the more we know about statistics, the better we can handle all this data, right? Question those assumptions, make informed decisions.
Great advice. Thanks for joining me on this adventure. And to everyone listening, get out there and explore that data.